Okay, stoichiometry. Heart and soul of chemistry, this is some heavy-duty chem math. So, you have already done some stoichiometry. And the kind of stoichiometry that you did before was what's called composition stoichiometry. You were just looking at how many moles is in 500 grams of sugar. If I have 3.2 times 10 to the 26th atoms of carbon, how many grams of carbon is that? That's compositional stoichiometry. And you did it initially with just simple elements, like the carbon example. Then you moved on to doing compounds and figuring out molar masses, and you're pretty good at that. What we're going to do now is called reaction stoichiometry, and it's the next step up. As you might guess, it involves, guess what? Reactions. So now we're looking at reactants and products, and we're figuring out the relative masses of those things. So you will, by the end of this, be able to know, because we're going to do a soap lab in here, remember, we're going to make soap. You will know, if I have 500 grams of soap, I need this much sodium hydroxide to react with it so that the soap I make doesn't burn somebody's face off. That's handy. That's good chemistry. That's good to know. It's good to be able to do that computation. Also, because many of you will probably give your soap to someone you love as a gift, and you don't want to burn their face off. Okay, there are 4 kinds of reaction stoichiometry problems that we can do. We can have a given and an unknown in moles. These are stupidly easy. These are one-step problems. You will not have a lot of them, because they're also kind of silly. Has somebody ever handed you a lump of something and you go, oh, this looks like, yeah, this feels like about 3 moles. No, we don't, typically in everyday life, we don't measure things in moles. We convert things to moles, but there's no device in this classroom that will allow you to measure something in moles. We measure things in grams all the time, though. We can do a composition stoichiometry where we have a given in moles and we're going to grams. We can have one where we're given a mass in grams and we're going to moles. And then number 4 is the most common type because it's the most real world of the 4. I give you a mass of something in grams. You tell me the mass in grams of product that can be produced. Or I give you a mass of a product in grams and you tell me how much reactant you will need to produce it. So those are the ones that you're going to see most often. Everything is in grams. These are, let's see, grams to moles to ratio to moles to grams. 4 or 5 steppers. Factor label. It's a big long factor label. They're really pretty, but they solve themselves if you set them up correctly. Okay, mole ratios. So you know what a ratio is. A ratio is a comparison of 2 units. 1 part this to 2 parts that. 2 parts that to 3 parts that. This is what you're going to use in every single problem that you do. Okay? You're always going to look for mole ratios. So because it can be used as a conversion factor. So let's think about the combustion of magnesium. A few of you seem to really like that. So we have 2 moles of magnesium plus 1 mole of oxygen yields 2 moles of magnesium oxide, right? What's the ratio, the mole ratio of magnesium to oxygen? 2 to 1. We have 2 moles of magnesium, 1 mole of oxygen. Sorry, you're right. What's the mole ratio of oxygen to magnesium? 1 to 2. It matters which one comes first. Depends on how the question is asked. What's the mole ratio of magnesium to magnesium oxide? This one's tricky. It's a trick question. Okay, go ahead and take a shot. It is 1 to 1. It's 2 to 2, and that simplifies. You know, if we look at those coefficients, we're getting the numbers for our ratio from the coefficients. So was everybody clear on that immediately? Because you know that the coefficient tells you how many moles of something reacts or is produced. So the ratio of magnesium to magnesium oxide is 2 to 2. We can simplify that down to 1 to 1. when you're setting up your stoichiometry factor label, I very often tell people, don't bother reducing, just pull your coefficients straight from the equation. And we're going to have some practice with this today. Just because it's a little bit less likely that you'll make a mistake that way. If you just pull your coefficients, when you get down to doing the math, you know it's going to cancel anyway. So that's a mole ratio. Okay, here's a big old equation. We have potassium hydroxide reacting with, that's phosphoric acid, H3PO4. It forms potassium phosphate and water. So in that case, potassium hydroxide is a base. Phosphoric acid is an acid. We're producing a salt and water. Okay. We have so many ratios in that equation, it's not even funny. So we can pull out from that one equation 8 different ratios, because there's a ratio of potassium hydroxide to potassium phosphate. And there's the inverse ratio of potassium phosphate to the potassium hydroxide. There's the ratio of potassium hydroxide to water, and vice versa. So for every ratio, there's also its inverse. That's the point. And every 2 things that exist in an equation have a ratio between them. If you're thinking about algebra and you're thinking about, they still do FOIL method and you do lines first, outside, inside, last. Okay. So you can do that first, outside, inside, last. Here, all you're doing for looking at these ratios is foiling. You're just looking at all the possible combinations, all the possible permutations that can yield up a ratio. Okay? Not too terribly difficult. Okay. Once you've got that ratio, you have the key to telling you how much product you're going to make from any quantity of that reactant. So using that same equation, if you're given 9 moles of potassium hydroxide, how many moles of potassium phosphate can be produced? Let's set this up as a factor label. In any factor label, what goes in our first box? What goes in our first box in any factor label? The given. So our given here is 9 moles potassium hydroxide. Okay. If we think back to everything we know about factor labels, we know that we want the same units and the same chemical in the next box down to cancel. What units, what chemical? Somebody with drawstrings.
Potassium hydroxide.
Potassium hydroxide, and what units? Moles. Okay? And we're going straight from moles to moles. So we're not going to have to do anything with grams. We're now looking for a mole ratio. What's the ratio of potassium hydroxide to potassium phosphate? For every 3 moles of potassium hydroxide, we can produce 1 mole of potassium phosphate. And that's it in this case. That's our whole problem. We started off with our given in moles of potassium phosphate. We know that we wanted to end up in moles, we started with our given in moles of potassium hydroxide. We know we wanted to end up in moles of potassium phosphate. That's it. We're done. So, with 9 moles of potassium hydroxide, we can make 3 moles of potassium phosphate. They're not all that easy, but that mole-to-mole ratio is at the heart of every single one of these problems.